Alright guys, welcome to part B of the cross product, also known as the vector product. In the last lesson we were looking at how to find the cross product between two vectors. Today we're going to be looking at an important result that the cross product gives us. What we're about to prove is that the modulus of the cross product is going to be equaling to the modulus of A times the modulus of B times sine of theta for all angles between 0 and pi. I'm going to use color coding to show some of the proofs so you can see where some of the results are. This is just really an algebraic process. There's nothing too much in it. So we know that the cross product is given by that equation over there. That was in part 1 of the cross product. And we want to find out what the modulus of that vector is going to be. So I'm going to use the modulus of the vector squared because that's going to get rid of that square root for us, and we can worry about that later on. So the modulus of the cross product squared is going to be the sum of each of its components squared, which I've done there. And I've tried to keep the color coding the same. Now, when you expand out those brackets, you'll end up with this long equation over here. And you can go through expanding out those brackets and making sure that your answer is the same as mine. All right, so we've got this nasty thing over here. Then what we can do is we can factorize a little bit. And this can all be factorized into this expression at the bottom here. Now, if you want to prove that, my suggestion would be to just expand out the bottom bracket to show that it's the same as the top line there if you wanted to. All right, so what you might notice here is that a1 squared, a2 squared, and a3 squared is the same as the modulus of a squared. And b1 squared, b2 squared, b3 squared is the same as the modulus of b squared. And this a1, b1, a2, b2, a3, b3 is the same as a dot b. So that's the modulus of a squared, that's the modulus of b squared. And if we do a1, b1 plus a2, b2 plus a3, b3, that's the definition of the dot product between those two vectors. And we're going to square that there. Now we also know that the dot product is also the same as the modulus of a, modulus of b, cos of theta. And what we're going to do is we're going to substitute that in for the a dot b, because we're trying to get to this result at the top there. So we've got modulus of a squared, modulus of b squared, minus the modulus of a squared, modulus of b squared, cos squared theta. And what you might also notice is that when we factor out the a squareds, b squareds, we have 1 minus cos squared theta. 1 minus cos squared theta is the same as sine squared theta. And remember that this is all the modulus of a cross b squared. We want to prove that just the modulus of a cross b is this result over here. Now, it's given that the angle is between 0 and pi. So when we take the square root of the left-hand side, we end up with the modulus of a cross b. And we need to take the square root of the right-hand side. When we take the square root of the right-hand side, we know that the square root of sine squared theta is going to be bigger than 0. Because when you square any number, it becomes positive. So it's got to be bigger than or equal to 0. And we know that sine theta is going to be bigger than 0 for 0 theta and pi. When you square root both sides, you'll end up with the required result that a cross b is the same as the modulus of a, modulus of b, sine of theta. Now, you don't need to prove all of that. All you need to know is that this formula can help us determine the angle between vectors a and b. So if we know the length of the cross product and we know what the length of a and b is, we can also determine the angle between the two vectors. There's another interesting result. If we know that the modulus of the cross product is this result over here, we can actually show that a and b will be parallel if the cross product equals 0. Now remember, this is different to the dot product, because when the dot product equaled 0, then we knew that a and b were perpendicular. Here we're saying when the cross product is 0, a and b are going to be parallel. So two vectors are parallel if the angle between them is either 0 degrees or 180 degrees. That means that sine of 0 is the same as sine of 180 degrees, which equals 0. So when we substitute the values of sine, which make two vectors parallel, into this equation here, what we end up with is the sine of theta will become 0 So it'll just be the modulus of the cross product between A and B is going to equal the modulus of A times the modulus of B times 0. 0 times these moduluses will also equal 0. The only way for this to be true is if the cross product of A and B equals 0 itself. Because if the cross product doesn't equal 0, then it has a length. And if it has a length, the modulus of that length won't be 0. This means that the cross product between A and B must be 0. Again, you don't need to be able to prove this, but it's an important result to know that if the cross product is 0, A and B are parallel. If the dot product is 0, then A and B are perpendicular. Alright, we're going to move into the last bit that we have to go through to do with this result that we showed before. What I've got here is I've got vector A, vector B, and I've got the angle between A and B. The length of A is defined by the modulus of A. The length of B is defined by the modulus of B. And the red line up here, this red vector, is A cross B. Now, what I'm going to do is I'm just going to extend, I'm going to project A across to the right hand side. I'm going to project B up to the top. What I've just made is a parallelogram because vector B is obviously parallel to vector B, vector A is obviously parallel to vector A, and the length of A doesn't necessarily equal the length of B. Then what I'm going to do is I'm going to think about it like that's the floor. So that's the plane that I'm going to be working on. The plane captured between vector A and vector B when it's been projected onto both sides. And this is going to be a parallelogram. Then what I'm going to do is I'm going to try and work out what the area of half of this parallelogram is going to be. So you can see that half this parallelogram is in the shape of a triangle. So we're trying to work out what the area of that triangle is over there. So we need to know two things for the area of a triangle. We need to know its base and its perpendicular height. We know that the base, I'm going to call the base A. We could have called it B, but we'll call it A for now. The base is the length of vector A. We need to work out what this perpendicular height is here. So what we've got is we've got a right angle triangle. So the height is actually going to be B sine of theta. Right, and that's just a bit of trigonometry to prove that result over there. So if this is the height here, we've got opposites and hypotenuse. So sine of theta is the opposite h over the hypotenuse, which is the modulus of b. The height is going to be the modulus of b times sine of theta. We've got this result over here. Now we're going to substitute this result into this formula. So remember that the base is the modulus of a, and the height is going to be the modulus of b sine of theta. The area of this half of this parallelogram, so the area of this little triangle here, the half AB sine of theta. Because A is the base and B sine theta is the height. Now just look at what happens when we double this area. When we double the area, we'll have AB sine of theta. Hey, that looks very similar to this equation up here. But when we double the area, we actually get the full area of the parallelogram. Now this is a very important result because that means that the magnitude or the modulus of the cross product or the length of the cross product between A and B actually gives us the area of the parallelogram determined by vector A and vector B, because 2 times the area is this result over here, which is the same as the length of the normal vector to A and B. What we can say is this is the third result from the day. The length of the cross product, A cross B, is actually equal to the area of the parallelogram determined by A and B. So if you wanted to find the area of the parallelogram determined by A and B, you just have to find the cross product of A and B and then determine the length of that vector. So the length of this vector A cross B is actually the same as the area enclosed by vector A and B. So a couple of things to take away from part B of this lecture. We know that A cross B is now the modulus of A modulus of B sine of theta. We can use this result to help us find the angle between two vectors given the cross product, or vice versa. What we've also shown is that when two vectors are parallel, A cross B must equal 0. The third thing we learned is that when we found the modulus of A cross B, we learned that that gives us the area determined by vector A and B. So if that's vector A and that's vector B, if we projected those two vectors, the length of the normal vector will give us the area enclosed or determined by vectors A and B.